Hi. Hi there. We are back. It's Wednesday, the 24th of September, 2025. This is my fourth stream in a row, too. Yeah, so here we are again. I think it makes sense to start off the streams. I mean, I'll probably come up with what I want to do at the start of the streams. But let's just talk about how you submit questions. Because my thinking is people should be able to, when they visit, I'm positive they can just scrub backwards through the stream, right? And so they can come back to the beginning and see the instructions. Maybe that way I don't have to feel like I have to give them over and over all the time. I'll just give them once at the beginning of the stream. So let's talk about it. I suggest you submit questions by going to thecalculustutor.com. Hold on a sec. Oh. There we go. So I'm going to put this in the chat and pin it. Submit questions. Submit your math questions for Ryan to answer. Calculus2.com. There we go. There's that. We'll pin it, pin message. So if you go to thecalculustutor.com, that's my website. Then what you will see there is this. There it is. There's the website, thecalculustutor.com. And the stream is just is right here. So, if you're just looking to watch it, boom, it's right there. I should probably add like a homework submission button right around here too, if this is where people are watching. But for right now, either click the banner at the top or this learn more button to the and again, streams available here. Has the schedule, and then so there's a couple ways to submit questions. My preferred way is this submission form. So if you click that, it'll open. You'll see if you're currently signed into a Google account and your Google account lets you access it. So like school Google accounts are sometimes locked down, and they sometimes don't let you access Google stuff that's not part of like your school Google organization. So if you can't access this, I don't know yet. Like I don't have a good way to test 4J student accounts. So somebody who tries this, I would love to hear back. Yes, you can access it with a 4J student account, student Google account, or no, you cannot. Because if you can't, I'll figure something else out. But suffice it to say, you need to be signed in because you're able to submit images. And I feel like that's really important, and I don't want to get rid of that. So long as you're able to sign in, you'll see this form. And then the form will walk you through the stuff. You have to, it's already collected your email address, so you'll just have to click to tell it yes, but you have to do that if you want to submit it. But yeah, and it just walks you through this. Who are you? What do you want me to call you when I, how would you like me to refer to you when I address your question on the stream? So the name you'd prefer me to use for you and pronouns, if you care. Yeah, and that'll help that. Let me know where the question came from. What class, like what specific class? Is it algebra? Is it geostats? Is it, calculus? And what instructor, what teacher. That's going to help other students find the answer to that. And I have some plans for how I'm going to use that data to sort of help organize answers. And then finally, and not finally, not quite yet, but the main thing, your actual question. What math question can I help you answer? What problem can I help you solve? Be as specific as possible. So don't just tell me, oh, number 8, and then include a page of your entire sheet or your textbook or what are all the problems on that page in your textbook. Tell me like, I had trouble with number 8 because it's asking about, because I think I need to use the chain rule, but I think I'm using it wrong. This problem about graphing, I know how to find the points, but my graph doesn't seem right, or something like that. Things like that. Be as specific as you can be. This will be augmented by the images you submit to help clarify your problem. So the images you should submit, you can submit up to 5 on this form. Obviously, the problem itself, whether it's in a textbook or on a worksheet or a picture you took of a problem the teacher posted to the board, whatever, send me that. Hopefully it's as clear and complete as possible, especially if you took it off of like the whiteboard or something like that. It may not be perfectly clear, perfectly in focus, or it might be partially cropped off weird or something like that. As clear and complete as you can manage. The clearer and more complete, the easier it is for me to give you a better answer. Complete meaning none of it's cropped out. So also include any diagrams. Also include the instructions. Sometimes the problem itself is separated from what you're supposed to do with those problems, especially on a worksheet or in textbooks. They'll have a block of instructions for like a whole bunch of problems. So if you just send me 39, but there was 10 of those problems and the instructions are way at the beginning of those 10 problems, I'm not going to be able to answer that question as well as I could, because I'm not privy necessarily to exactly what it was asking you. So if your picture can also include the instructions, any diagrams, and then also if you send me a picture of your work, the work you've tried so far, even if it's wrong or you got stuck or you feel like it's wrong or you feel uncertain about it, my promise to you is I will never show your work on stream, which means if you tried to take a picture of the problem but it includes your work, I will do my best to either crop that out of the picture you send me before I show the picture of the problem, or I will do my best to sort of transcribe the problem in such a way that it doesn't expose your work without permission. That said, if you're totally fine with me showing your work, include that somewhere in here. Say you can show my work, that's fine. Include it in like your problem description or something. Yeah, this is the preferred way. You should be able to hit submit. I will get an email notification, but I also have the back end of this form pulled up, so I should be able to see pretty quickly when problems come in here, and I should be able to sort of jump right into them, assuming I'm not right in the middle of another problem. All right, let's say though, because I haven't had a chance to test this with 4J student accounts, go here and you try to go to that form. Actually, if you're not signed in, you'll just get a sign-in window, and if your school Google account won't play nice, you'll just have some sort of like message here that tells you like that your organization doesn't allow you to access forms that aren't part of your organization or whatever. If somebody were to send a screenshot of that to me, maybe via email or something, that would be fine. That would let me know a lot. Anyway, that's what you'd see. So here, let me share my screen again here. But let's say for one reason or another, I mean, feel free to if you have another Google account that's not your school one, you can use this form. It doesn't have to be your school account. You can always just email them directly to me. at ryan@thecalculustutor.com. Pretty straightforward email address, right? And then here, because the form guides you through submitting a good question, so I can give you a good answer, since the email is more freeform, right? Here's the guidelines. 4 parts, just like the form. Tell me how to address you. Tell me where the problem came from. Ask me a specific question, as specific as you can, and attach clear, complete pictures of the problem, the instructions, any diagrams, and potentially your work. And same promise here. And then those will come in my email. Email can be a bit slower. So, give it up to a couple minutes, especially because there's images attached. Give it a couple minutes before you might expect me to see it. But that's the process. That's how we get started here. 12 minutes is way too long for that, right? I'm being way too specific. I'm guiding you through it. You all can likely manage a Google form, and if you can't, chat. That's what chat's for. If the email or the Google form submission is just not working for you, if you feel like, or if you just don't have a way to get me the problem, let me know in chat. Send me an email and tell me that. I'm excited to figure out other options for people to submit problems. We could do a Discord. I could do a subreddit. There's all sorts of ways. Additional ways. I don't want to have too many avenues, though, because I then have to monitor all of those channels. And the more channels I have to monitor simultaneously, the more likely it is your problem will either get missed or it'll take me a while to get to it. And it becomes way harder also to sort of keep track of the order in which the problems come in. So, because I'm more or less going to try to be, answer questions in the order they come in. That seems like the most straightforward way to do this. I told myself, though, I committed before this stream, after yesterday's stream, I committed that I wanted a lot of this stream to be doing some math, though. So here, when I get questions and I'm giving answers, here is largely, this is going to be a huge portion of what you see on this channel, I imagine, is this sort of off-white gridded background and then my face small. So what we need, there we go. We need a problem to work on, right? Let me grab one. So let's start with some calculus, shall we? I'm always down to start with some calculus. I'm trying to choose. I'm getting picky about which one I choose. Here we go. We'll grab this. We'll go here. And here we are. This will be our first question. I'm going to have some way I want to like organize these. I need to have I need to have the problem to solve. It's just, it can be really tough to solve a hypothetical problem that you know you will eventually really have. All right, looking at the feed here, I probably need to make these a little bigger when I do them, right? There we are. All right. Find the value of C guaranteed by the mean value theorem for this integral here, which is the integral from 1 to 4 of 2 plus 3 root x. All right, so we have a definite integral. It's an integral with a square root. So not terribly advanced, but definitely not week 1 integral calculus. We should probably remind ourselves of what this mean value theorem is, right? Do one of my favorite things. Grab something somebody else has already made. Okay, we'll be able to sort of ooh, you know what? Let's open. I'm going to take stuff from the OpenStax calculus textbook. I should probably review the license for this. That you are free to use and adapt, but not for commercial purposes. Huh. Free to use and adapt, but not for commercial purposes. I'm not charging for this. I'm not getting any cut of the ads or anything. I would say this is purely educational purposes. Excellent. This seems like a good source for this sort of stuff. Mean value theorem. So the mean value, well, I'm looking this up to get just like a nice graphic and stuff like that. The mean value theorem basically just says that over the course of a curve, a function, sorry, getting distracted. So if you have, you have any old function, right? It can be curvy, it can be straight line, increasing, decreasing, whatever. The mean value theorem just says that if it's continuous, so it doesn't break, like it doesn't have any like open dot holes, it doesn't have any asymptotes, those are all discontinuities, it doesn't have any jumps, anything like that. It has to just be a fully continuous curve over some interval. Then the average, so whatever values the function has, right? It could be, at the beginning, it could be equal to 2, and then it could go up to 5, and then come down to 3, and then it could go up to 7, right? Things like that. What of all those values, whatever the average value of that is, and we can calculate it. We have ways to calculate it. The graph has to go through that value. So if you calculate that the average value is, say, 8 on that curve that we're talking about, right? Then the function has to be equal to 8. There has to be some place in there where over the place where the average value is 8, that the function is itself equal to 8. Some x value you can plug in so that f of that x value is equal to 8, right? And that's all the mean value theorem basically says. So I'm going to grab, this is in the OpenStax textbook. I should have a resource someplace, resources. I'll have a resources tab on the website at some point. Let me grab this. So here's our mean value theorem. Precisely stated, right? What I just gave you all was like in a summary overview, and those are really important. We need to understand what these things mean on an intuitive level. We should be able to explain them, or we would like you to be able to explain them. We'd like you to be able to get comfortable enough with these things that you could explain them to, like, you know, a fifth grader or something like that. They don't have to be able to compute it. We just want you to be able to explain the idea like I did, that like if something is continuous from here to here, and we look at whatever its average value is, well, it has to go through that average value. It couldn't just skip over it, because the only way to have an average is to have values above and below it. And if it's continuous, to get from those lower values to those higher values, it just has to go through that value, or through that average value, because the average is always going to be in between. All right, so here is it precisely stated according to the OpenStax open source calculus textbook. This is the mean value theorem for integrals, but that's what we're talking about here. So if a function is continuous on some interval, then there is at least one point, I didn't specify that, there's at least one point within that interval, so interval from A to B, there's some x value bigger than A but lower than B, we'll call it C, some value in between there, that if you plug that value into the function, you get, and this is the formula for the average value. So it's exactly what I just said. There's a place where the function is equal to its own average value over that same interval. Notice A and B here, A and B here. So let's label this right here. This is the average value formula. So if you want it, as we talked about, there is a way to find the average value of a function. This is it. To break this down, b minus a, that's how wide the interval is, right? If a is 2 and b is 5, that's an interval of size 3. 5 minus 2 is 3. They're 3 away from each other. So that's all this is. This is a way to use multiplication, but turn it into a fraction to divide. We're just dividing by the width of the interval, right? Whatever number this is, when we divide it, when we multiply it against this fraction, it'll go up here. So this is dividing by the width of the interval, and an integral always is always a summation. It always adds together. That sometimes we call it the area under the curve. It adds together the continuous values of the integral, or of the function, from a to b, and that's what a definite integral does. We can conceptualize this as area under the curve, but in more direct mathematical terms, it's a continuous summation, a continuous adding of all those tiny little individual y values. And this is how you add them up. And then you divide it by how wide the interval is, and that gives you the average. Just like the classic statistical average that you might have learned, where you add all the stuff up. That's what the integral does. The integral adds all the stuff up, and you divide by how much stuff is there. And that's why we're dividing by the width of the interval, because that's how much stuff is in the interval, is however wide it is. So that's our average value formula. Excellent. All right. OpenStax also gives us this other one where they solve for the integral, right? This can be nice. And in fact, might be helpful for us. Let's see. So let's go. Now that we have this mean value theorem that this problem number 3 is referring to, now that we know it's just talking about, so when it says find the value of C guaranteed by the mean value theorem, it means this value C, right? It's convenient that this problem is using the same notation as this math book. But this C, we could call it anything. But yeah, they want us to find the point C on this for this function right here. That's our f of x. Let me label that. Right, this right here. This is our f of x. This is our a. This is our b. Right, a and b. And so we know, so the way they presented this integral actually gives us a nice place to start. Let's take that integral 1 to 4 of 2 plus 3 root x, 2 plus 3. And instead of root x, I'm going to write it as x to the 1/2 power. Right? If you need that reminder, we can put that over. We can put that over here to the side. We can say, remember, root x is the same thing as x to the 1/2 power. Boom. All right, there's a little note for us that that's true. Do that. There's our dx, and that's going to equal, now we know what f of x is. It is this function. So what I'm going to do here, when I set this up, I'm not going to write f of c. I'm going to write the function 2 plus, and instead of x, or 2 plus 3 times, and instead of x, I'm going to go ahead and substitute the c we're looking for, and it's c to the 1/2 power. And then, of course, it's times b minus a. We know b is 4 and a is 1. Excellent. So on the left, we have a definite integral with which, assuming this integral exists over that interval, then that will just come out to some number. So the left-hand side of this is just going to be, oops, let me move my cursor. Oh, feel free to put in chat, your cursor's in the way, your cursor's in the way. That's going to happen. So on the left-hand side, we have an integral that's going to, when we evaluate it, it's going to come out to be just some number. We don't know what number yet. And on the left-hand side, we have an equation that only has one variable. And so we'll be able to, simplify, move stuff around here and simplify. But then we'll just have a really pretty straightforward equation to solve for c. Let's keep going. Let's see what happens. May as well do the integral first. So I guess maybe we'll remind ourselves how you deal with a definite integral, right? Which is an integral that has these boundary values. So from a to b, if you have some f of x dx, then that definite integral is always going to be equal to the, so we're going to put capital F for the antiderivative of this function at b minus the antiderivative of a. This is our fundamental theorem of calculus. So we need to know what is the antiderivative, so we can do that substitution. So the antiderivative of 2 plus 3 x to the 1/2. Well, the antiderivative of a constant just gets the variable. So that's 2 times x. And here we're going to use our power rule, which basically just says, and we can put that over here. So if f of x is equal to ax to the n, so some number times the variable raised to a power, then the antiderivative, actually, here's how we'll write this. We'll just do it like this. Ax to the n. There we go. That will be, we'll end up dividing by one more than the original exponent, and then that exponent will increase by 1. So you end up dividing by the new exponent is another way to say that. Excellent. I do want to start increasing those a little bit. There we go. Okay, there's another little note for us. The light blue, I'm going to try to be consistent about this. I probably will. This is the thing I do with my one-on-one students. This is the color I use for the notes that would be good for you to either be aware of and have collected together in your own notes, or possibly even memorize, especially if your teacher doesn't let you use any notes. Push back against that if your teacher doesn't let you use notes. Oops. There we go. Oftentimes teachers have a decent reason for not letting you use notes. But I don't like it. It feels contrived to me. All right, so let's get back into this. I erased the little work I'd done because I sort of diverted to make some notes. So let's talk about this again. We're going to take the antiderivative. We're trying to find the antiderivative of this 2 plus 3x to the 1/2. So the antiderivative of 2 is 2x. Constant just gets the variable. And then so our power rule here says that we should take this exponent, add 1 to it, and then we divide by that. So here's our 3, and we're going to divide by 1 more than 1/2 is 3/2. And then this will become x to the 3/2. Awesome. There's x. Technically, there's a plus c here. You might remember from your indefinite integrals. We're going to end up plugging values in, so those c's will cancel out. I just wanted to find this separately. Let's simplify this, I suppose. If we're going to be plugging values in, we may as well. I talked about fraction division in, I think, my very first session, my very first stream. Yeah. So you can refer back to that. When we're doing things like calculus, I might skip past how to do these things for the sake of time, because that's oftentimes not where the people asking the calculus questions are getting hung up. But in chat, you can always let me know, like, hey, can you show how you did that fraction division? How you got, well, I'm going to show you right here. 3 divided by 3 over 2, that becomes 2. How do we know that? 3 over 2 is 1.5. How many times does 1.5 go into 3? It goes in twice. There we go. There's a bunch of other ways to do that. That's the way I did it. And now we have this. Huzzah! Okay, we could like factor out a shared value. That's overkill. So here's what we're going to do. We're going to figure out this integral right here. We know that it's going to be 2 times 4, because we plug in b first, plus 2 times 4 to the 3/2, minus 2 times 1 plus 2 times 1 to the 3/2. And there we go. So this will be 8. 4 to the 3/2. The half power tells us take a square root. Square root of 4 is 2. And then the 3 tells us raise that to the third power. 2 to the third power is 8. 2 times 8 is 16. So this will be 8 plus 16 minus, this 2 times 1 is 2. 1 to any power is itself. So this is 2 plus 2, which is 4. 8 plus 16 is 24, minus 4 is 20. And there we go. Like we talked about, the left-hand definite integral just becomes a number, and in fact, it becomes 20. So now if you're trying to sort of follow here, we're going to jump back down. And we can say that this is 20 equals, and now over here, now we need to like simplify some stuff. 4 minus 1 is 3. I guess we may as well start there. So we'll do 2 plus, oh no, that's fine. 2 plus 3c to the 1/2 times 3. Boom. All right, there's a few ways to do this. Since we're trying to solve for c, so we could distribute this 3 in here. But since we're trying to solve for c, let's just divide it away so that we don't have to deal with it anymore, right? So we're going to do divided by 3 on this. Ooh, that's very light. We'll do divided by 3 here, divided by 3 here. Certainly, 20 over 3 is a fraction. It makes things more complicated, but don't worry terribly about the fractions. If a fraction comes up, use it. Keep moving along with the problem. And if you get in a situation where you have to do something kind of complicated with that fraction, just take it slow. And if we have to end up doing anything complicated with this fraction, I'll be able to demonstrate that. But oftentimes you don't. Or you don't have to do anything terribly complicated. So over here, all that we're left with is 2 plus 3c to the 1/2. I say all, but we still have 3 steps left. Let's subtract the 2. But since we know, okay, we're already to a point where we're going to have to start doing some complicated stuff, right? Subtract 2 from this side. I want to subtract 2 from this side as well. But this is a fraction. And so I'd have to do fraction. So let's be aware that it's a fraction. Let's subtract 2, but express it as thirds. If I were to write a fraction with 3 on the bottom, but the fraction's simplified to 2, I'm going to do it when we get over here. I'm going to start needing some to figure out what colors mean and stuff like that. But let's see. So we know something over 6, we want it to equal 2. Or sorry, something over 3. We want it to be thirds. Oh, I just stepped on the punchline. Right, we want it to be thirds, we want it to be equal to. So that has to be a 6. So we will say minus 6 thirds. Instead of saying minus 2, because it's the same thing. It's the same value, just written differently. And now we don't have to take a whole separate step where we deal with that fraction division. We just sort of incorporated it into this step. 20 thirds minus 6 thirds. Well, if I have 20 of these thirds and I take away 6 of them, all I have left is 14 of those thirds. And then over here, we're left with 3 times c to the 1/2. C to the 1/2. Excellent. All right. What do we do to continue along there? Well, we'll divide by the 3. Boop. Now we have, because this is a fraction, right? So we are ending up having to do complicated things with this fraction. Is there another way to get rid of this 3 rather than dividing by 3? So we don't have to do this fraction division stuff, which we could do, right? But do you know other ways to do things? What if we instead multiplied by 1/3? What's 1/3 times 3? Well, it's 1. 1 times anything is itself. And that's what it means for things to cancel out, is if they're multiplying, they become a 1. If they're adding or subtracting, they become a 0. And that's all it means to cancel something out. So we multiplied this side by 1/3, so we'll also multiply this side by 1/3. Multiply fractions straight across, we get 14 over 9 equals c to the half. Oops, I wrote a 6 there for some reason. C to the 1/2. 2, 6 thirds. Yeah, I think. Yep, this seems like it's going well. Sorry, I should verbalize when I'm doing this. I just went back really quick to look back through the work. I see where we're going. In order to undo this 1/2, we're gonna, okay, so it won't be that big a deal. Okay, never mind. Sorry. I thought we were gonna have to take a square root. It's already a square root. let's continue. C to the 1/2, we want to solve for that C, so we will raise it to the second power. Remember, this is a square root. It's just a different way to write a square root. How do you want to do a square root? You square it. Also, how do these combine? An exponent raised to an exponent, you multiply them. 1/2 times 2 is 1, so this will become C to the first, which is just C, which means that canceled out. But it does mean we have to also square this. So over here, 14 times 14, 200 and... No, I don't think it's 200. It's 100. 15 times 15 is 225. It's 196, I think. I have a calculator right here. Yeah, 196. All right, this is 196. The way you square fractions, right, this is 14 over 9 times itself. So 14 times 14 over 9 times 9, 81. We can know, so this is equal to C. We can know this won't reduce because the only factors that go into 196 are 14 and itself, and 14 is only made up of 2 and 7. The only thing that goes into 81 is 9, and 9 it's only made up of 3 and 3. So they don't share any factors. We got to C. And here's a really important thing. I'm going to take my green, which is my, we're done. Here's my answer. And I'm going to underline it. I'm not going to box it yet because this is the end of this process that I just went through. I was explaining stuff as we went. It's been a little bit since we looked at what we were actually trying to figure out. So now we found that this C value in here is equal to this fraction, 196 over 81. But what was that C value supposed to be? The value of C guaranteed. Oh, by the mean value theorem. Oh, that's the X value that if you plug it into this function, it will give you the average value, which we figured out is actually 20, by the way. We didn't label it here, but it could have been worthwhile. This is the average value of f of x equals 2 plus 3x to the 1/2 on 1 to 4. Boom. That's literally what this number means. Oh, wait a second. Hold on. It's not. I'm so sorry. It hasn't been divided by the 3 yet. The 20 over 3 is technically the average value. And that's a little bit harder to tell. Regardless, so this is our average value. So if we plug 196 over 81 into that function, and we can test it. This is check our answer. Does f of 196 over 81 equal 20 over 3? Well, let's see. F of x was 2 plus 3 root x. So 2 plus 3x. Let me show you something really quick. This is something I hope to do a bunch of, show you cool tools and stuff. Let's look at, I use the Desmo Scientific Calculator as my daily driver calculator, especially when I'm tutoring, because I can have it up on my screen, right? And I can share my screen. So let me share and reshare and find a window. Here we go. And I'm just going to share. So it's going to look, there we go. Here's the Desmos calculator I'm using. So check out what I can do. There's the function f of x. And now I'm going to type in f of 196 over 81. Oops. It gives us this weird decimal. This button right here converts to a fraction. Oh, look at that, 20 over 3. Boom. So here's what I'm going to do. I'll grab this right here. And I'll stop the share on the calculator so that I can restart the share on our notes. And we'll just paste this in here. Oops. And the answer to our, yes. Awesome. So that means this is our answer, but actually here's what I'd like to do. So I encourage you to do this. You don't have to do this on your actual homework that you turn in. Just do it in your head. I'm going to actually write it out, but at least do this in your head. Now that we've done this, we've taken a minute to check our answer. Now we want to tell ourselves, what did we just find? So we can say the mean value theorem in VT, that's totally fine, says that for for f of x equals 2 plus 3 root x, the average value is found at x equals 196 over 81. And this is the answer I'm going to go with right here on this stream. Because math is something we use. It is a tool. It's a communication tool. That's what I'm trying to get at. And so what I want to encourage you to do is learn to communicate with it. Now, math classes don't teach you this very well. We've tried, right? You've definitely had teachers that told you state your answer in a full sentence, or maybe you haven't. I did, but not very many of them. But they tell you use units or just all these little things that feel like the teacher's just being picky or overly precise. They're not. It's an attempt to teach. That's the teacher's one attempt, or not one attempt, but like it's the teacher trying to sneak in a way to teach you math as communication. It's to try to teach you good communication habits when you're doing math. But the way we teach math so often emphasizes just getting to the correct answer the correct way, that we just stop right there at 196 over 81 equals C and say that's the answer, as if the answer is the goal of math. And it's not. The goal of math is to be a useful and robust tool for investigation and to help us make accurate, reliable, repeatable decisions. Math is a tool that lets us avoid sort of the randomness of, sorry, bunch of hairs, of just sort of bumbling through. That's really what it is. It's a way for us to try to make accurate predictions for the most part. And to make sense of the world and feel like we understand how the pieces fit together, how one thing leads to another. All right, calculus problem. Fantastic. Mean value theorem stuff. What else? Let's see. Let's find. Oh, what about solving rational equations? I have some notes about that in here. Oh, this is like a big thing. This could be actually a good thing for tomorrow, maybe. Just to like focus on largely, like let this be. Okay, that's interesting. I'm looking back through some old student notes. See good problems I've already worked on with students. While I'm doing that, I'll just go back up here. Remind you, you can submit your questions at thecalculustutor.com. Actually, why don't I do this? I'll do copy. I'll go back down. I'll put it here. My cursor out of the way. Also like to, a little thing I kind of do for myself here is bundle all this stuff together into like one little thing that I can move around. So let's do that. There we go. Boom. Submit your math questions at thecalculustutor.com. Easy, easy peasy. Ooh, logarithms. Yes, yes, yes. That's a good thing to talk about. Okay. Let's justify logarithms. Please submit your questions at thecalculustutor.com. has an email. All right. Confirmation from a student. Love to see it. Okay. Let's check the submission form. Reload it. Okay. Very good, very good. Okay. Then I think we are free to why are logarithms is what we're talking about. So maybe you don't even know what a logarithm is. Maybe you've heard of a logarithm. You don't remember really what it is. Maybe you've been using logarithms recently and you don't know what they are. That's sort of the only option for me when engaging with people. I would bet money that if I just encountered a random person on the street, I would bet money that if I asked them what a logarithm was, that they wouldn't be able to tell me. Accurately, at least. No shade. That's fine. I'm just merely acknowledging that fact. So before we even get to the why are logarithms, or to the what are logarithms of it all, let's give ourselves a reason to need them. Here is a vague population is growing a vague population is growing according to the equation P of t, so the population at time t equals 100 times 1.8 1.08 t. We'll just say t. We'll just say t. Actually, it doesn't need to get more complicated than that. We'll just say t. Okay. We're not going to bother to, in this moment, we're not going to address where this equation comes from. I made it up. But it is roughly the shape of an equation that could model a population that is experiencing literal, not the way it's commonly used, but literal exponential growth, which is a thing that populations can experience in the right circumstances. Okay, a vague population is growing according to this equation. When will the population reach 250? I'm making every aspect of this up, right? Not picking numbers that can come out nicely. So super contrived, but I would still argue representative scenario. Suffice it to say, we can model population growth using equations. Populations can experience exponential growth, so there might be a period of time where this is the a good equation to model that population's growth. It probably wouldn't be the best equation in the long run, but over a limited period of time. It's also very sensible to ask when a population will reach a certain amount, right? For whatever reason, if it's, I grew up in Southern Oregon, definitely east of the Cascades, and so we hunted deer and things like that. And deer are hunted as part of the effort to control their population because deer breed quickly and aggressively. So hunting is a way to control that population. And so you have a whole governmental department and a whole population of people who are concerned with the population of an organism, right? So very, very sensible question to be asking about a semi-realistic, at least representative equation. Okay, so we're asking for time. So easiest way to do this, so this is asking when the function, the p part, will equal 250. So we can do 250 is equal to 100 times 1.08 to the t. All right, so we want to solve for t. Well, 1.08 raised to the t, but it's being multiplied, so we know we have to get rid of that multiplier. So we'll do divided by 100 and divided by 100. Cancel out. And so over here, we'll be left with 2.5. And over here, we're left with 1.08 to the t. And now the question becomes, how do you solve that? This is 1.08 raised to the t. Let's remind ourselves what an exponent actually means, right? So like if we had some number like 5 raised to the third power, that means 5 times 5 times 5. Exponents don't have to be whole numbers or positive numbers. So, if you had a number like, actually we dealt with this earlier, a number like 3/2, what that actually means is the square root of 5, because that's the 5 to the 1/2 part. That's what the 2 in the denominator does. And then the 3 tells us to multiply that 3 times. Root 5 times root 5. So that's what that would look like, right? So exponents tell you to multiply over and over again some number of times. They potentially tell you to also take a square root, and that's what you're multiplying by multiple times, is whatever that root is. So we want to know, what number do you raise 1.08 to get 2.5? Well, we can know a few things. We know that t has got to be greater than 1. T to the first power, or anything to the first power, 1.08 to the first power would just be itself. And that's not big enough. We need to get bigger. We could, here, let me go back to my calculator. I'll do 1.08 squared. So we also know t needs to be greater than 2, because 1.08 squared is equal to 1.1664, right? Okay, and we can sort of keep doing this. In fact, what if I do to the 5th? What if I do to the... In fact, we could keep doing this. This is kind of a way to solve this problem. We can figure out that 1.08 to the 11th is equal to 2.33. And 1.08 to the 12th is equal to 2.52. And so, based on this tells us that t is somewhere between, t has to be greater than 11, but it has to be less than 12. Because if it's 12, it's bigger than 2.5. Not much bigger, but still bigger. We want it to be exactly 2.5. And 11 is too small. It's only 2.33. So we know, okay, so we could try 11.5, and we could zero in like this. This is a binary search is essentially what's happening here. And we can get as many decibels of accuracy as we want, but it's tedious, and there's no good way to. And I don't want to say that there are good ways to summarize this, but not that math teachers and students would like. You can summarize it with programming, computer programming. So we have this slow, tedious process where we can just, is it bigger than this? Is smaller than this? Bigger than this? Smaller than this? Bigger than this? Smaller than this? We can go back and forth, and get as many levels of accuracy. We can say it has to be between 11 point whatever, 11.1 and 11.9. I'm not sure. I haven't. Maybe I'm wrong there. So it would be nice if there was a more straightforward way, if there was something that existed in math. And so part of the reason we have to do it this way is because, at least without logarithms, there's no way to cancel out this 1.08 that's in the base of an exponential. Now, if this was reversed, if it was t raised to the 1.08, we could take the 1.08th root. Right, and there's a way with just exponents to sort of cancel stuff, or exponents and roots, but not here. There's we don't know what t is, so we'd have to take like a t-th root, and if we did that, we just end up with the t-th root of 2.5 equals 1.08, right? And we took the t from being up here in the exponent to now in this weird, what we call that the index position of the root. I don't think it's going to be easier to solve for t there. Okay, so we have a way we could get there, but it sort of it requires us to divert from our usual algebraic process. So it would be really nice if there was an algebra step we could take here that would let us just, like algebra does, let us move some numbers around. Right here, this was 100. This was 100 times multiplying something, so I divided because I know those are inverse operations, and this will result in 1 times that, which is itself, and therefore cancels out. And we know anything I do to one side, I have to do to the other. So this is where logarithms come in. So this right here is a process called exponentiation. And it's really what's happening when you raise anything to an exponent. But when the exponent is a concrete number, a 2, a 7, a 3.9, whatever, but a known value, there's nothing to figure out. There's nothing to solve. There's nothing to necessarily move around. You can either manipulate that known value with other exponents and roots, or you can just raise whatever value to that exponent if you know what both of them are, and you just get a new value. It's easier to deal with. So this is our issue that we're trying to deal with, is exponentiation. We can't divide by anything, multiply by anything, add or subtract anything that will get this t by itself from here, unless we introduce logarithms. So here is where we justify logarithms. So if we have it, so I'm going to make us some notes here. If you have an exponential, or rather, if you have an equation in exponential form. So I'm going to summarize that, and I'm going to color code some things here. So you have some base value that I'm going to call b. It's raised to some exponent that I'm going to call e. Actually, let's work with all capitals here, b. And then it's equal to some other value. I'm just going to call that p. For product, I forget, I don't remember what you call the result of exponentiation. I'm sure it has a name. Okay, this is one form. Something you may have talked about in middle school. I know I taught it when I was teaching middle school. Was fact families. And even if this doesn't sound familiar, you know this idea from doing algebra. Fact families are the idea that when you combine two numbers with a math operation and it equals some third number, the relationship between those three numbers can be expressed in multiple ways. The example I like to give is 3 times 5 equals 15. I think we can all agree that that's true. That's not the only way to write that, right? We could also write 3 times 5. Oops, that's the same way. I could also write 5 times 3 equals 15. We're like, okay, I mean, yeah, that's basically the same thing. It's just multiplication. We know you can do multiplication in, you can multiply numbers in either order. That's a property of multiplication. But there's two more ways to write the relationship that 3, 5, and 15 have to each other. So these three numbers have this particular relationship. That if you multiply these two, you get this one. But that means that if you take the bigger one, or the result, the product, and divide it by either of those, you get the remaining factor. And if we can write that, that means we can also write this. And so this is generally referred to as fact families, right? So if 3 times 5 equals 15, that's what we call a math fact. And there are families of them. And so if your fact family is built around multiplication, you will also have ways to express it with division. If your fact family is built around addition, so 2 plus 9 is 11, well, there's also subtraction. 11 minus 9 equals 2, right? So there are pairs of inverse operations that create, and that's basically what creates this phenomenon, or the fact that there are fact families. Notice here, when we're dealing with exponentials, that we have three values that are being related. We don't have a symbol like multiplication, division, addition, or subtraction. Instead, we have just sort of this notation where if you take one number, oops, I'm going to make this a little nicer, and you write it up to the right, above, and make it a little smaller, we know that that means you're taking this base number, and going b times b times b until there are EBs being multiplied here. And if it's a fraction or a decimal, we know that there's some root taking going on as well. I still don't like my E there. Okay, we'll just have to deal with it. So this is just exponentiation is a fifth math operation that you've been taught now. It may not have ever been called an operation by any of your teachers for whatever reason, but that means there is an inverse operation, a complementary operation. Based on where this started, can you guess what it is? It's logarithms or logarithmic equations. And just like you can rearrange the values of a multiplication fact and change the multiplication to a different operation and rearrange them, and it's still true, we can rearrange these values, and instead of using exponentiation, we'll use a logarithm. So here's what that looks like. I'm going to move this. Oops. Move this arrow over just a little bit. So logarithms don't have a nice symbol like a dot or an X or an asterisk or a this sort of symbol or a diviculum, a dividing line, or a plus sign or a minus sign. They just use function notation, which is going to be a topic we'll talk about elsewhere, and I'll probably bring up logarithms. But that is to say, if you want to say you're taking the log of something, you literally write the word log, and then all logs, there's an infinite number of types of logarithms. They are defined by their base number. Oh, and this is the same b, log base b. And then there's parentheses, just like a function f of x or sine and cosine, right? So this is telling us what log we're using. We're using log base b. I'm trying to write this as nice as possible. There we go. And then what do we take the log of? Well, we take the log of this p-value, this product. So the result of exponentiation is what you take the log of. And if you take the log of that value, what does it give you? Well, the only third value left, it gives you the exponent value. And so what logarithms do is a logarithm answers the question, what exponent would you have to raise b to turn it into p? So if you just see log base b of p, and so we can do like a little example here. Actually, we'll use our one that we already have as our example, of course. So we have 2.5. So I'm going to rearrange this. I'm going to put the exponential on the left-hand side like I did there. And I'm going to, so we have 1.08 to the t is equal to 2.5. And according to this, if this is true, then we should be able to rewrite it with a logarithm. So the log is going to be log base 1.08. And that's totally fine. Base numbers on logarithms, they just have to be positive, but they can be decimals, fractions, whole numbers. Okay. What are we taking the log of? We're taking the log of this 2.5. And what does it equal? It equals the thing we were trying to solve for, t. And now check out what we have. We've gotten t was in the exponent. We didn't have any way to access it. We kind of figured out a way we might be able to like get to the value of t by going back and forth. But we didn't have an algebraic way. We didn't have a way to say t is equal to this particular math expression. Now we do. Now here's the question. You're like, oh, okay, but I still don't know how to figure out what the log of 1.08 of the log base 1.08 of 2.5 is. And that's true. However, and honestly, nobody would. Well, I don't want to say nobody, but like nobody expects you to be able to do this particular logarithm in your head. So we can enter it on a calculator. Let me if I do that, helps if I enter the correct numbers though. And so if I do that, I get all of this is equal to 11 point, I'm just going to call it 11.9 equals t. And check that out. That is between 11 and 12. It's actually really close to 12, but that sort of makes sense because remember when we plugged in 12, we got 2.52. So we should probably have expected the answer to be really close to 12. And there we go. So after 11.9 whatevers, did we say what t was? No, I didn't define what t was. This is not a greatly formed question. I just wanted to have the equation. I didn't want just a totally meaningless equation. I wanted us to be trying to answer some sort of question. So what we can say then, our answer is the vague population will reach 250 when t equals 11.9. We don't know if those are hours, days, weeks, seconds, eons. It doesn't matter. It wasn't specified in the problem. Whatever they were, it would be 11.9 of them. And there we go. How I enter that into my calculator, things like that, is definitely worth going over, I think, especially since we have a couple minutes here. So first of all, let's do some examples, huh? So let's do the log. So follow along. Cool. The log base 5 of 25. So remember, a log is asking the question, what power do we raise 5 to get 25? That's supposed to be a comma, right? Or another way to say it is 5 raised to the question mark or x or whatever equals 25. Remember, this is just rearranging. This is over here would be a question mark, and we can rearrange it to say 5 to the question mark equals 25. So whenever you see a logarithm, if you're maybe feel like you're struggling to understand what it's asking, rearrange it into an exponential, and it will make more sense. We have a more intuitive understanding of what exponentials look like and how to work with them. Mainly because you've actually been working with exponents for a while, and that gives you a lot of tools to deal with exponential functions. The only tool it didn't give you is a true proper inverse until now. Now there's logarithms, and now anytime you see an exponential, you know there's a corresponding logarithm. Anytime you see a logarithm, you know there's a corresponding exponential. So to go back to this question, 5 to what power equals 25? Well, that would have to be 5 to the second power. All right. So log base 5 of 25 equals 2. So when these are straightforward, you can do them in your head, just like any other math operation, right? If I asked you what 3 times 4 is, many people out there probably pretty quickly said, oh, that's 12. I know that's 12. So you can get to the point now, like if somebody gives me a log, even if it's one that doesn't work out perfectly, I can tell you, like we did with the t, I can usually tell you, oh, I'm not sure what that equals, but it's between these two numbers, somewhere in there. Okay, what about log base? These are tough because exponential values get big really quickly. What about log base 3 of 3 or 4? 343? Is that the number I want? 243. I want 243. There we go. Oh, yeah, that makes way more sense. 243. So what power do we raise 3 to get 243? 3 to what power equals 243? Now, this one, you might not know this one off the top of your head. You might know that 3 to the second power, 3 squared, is 9. You might know that 3 cubed is 27. You might even know 3 to the fourth is 81. So what would 3 to the fifth be? Well, it would just 3 to the fifth would just be 81 times 3, because 81 is already 3 to the fourth, right? And 81 times 3, 80 times 3 is 240. 1 times 3 is 3 is 243. Oh, so this has to equal 5, because 3 to the fifth power is 243. Here's a little bit more challenging one. Log 1/2, 1/8. Ooh, fractions. Same question. We're still asking 1/2, a fraction certainly, but raised to some exponent is equal to 1/8. That's still the question we're trying to answer. We're still trying to figure out what exponent would this have to be. There's a few ways to go about this, but we know if you're multiplying powers of 1/2, it's just 1/2 times 1/2 times, over and over and over again. So it's just 2 times 2 times 2. So really, this is kind of a way of asking 2 to what power is 8? Well, that's 3. It'll be the same thing here. Right? 1/2 times 1/2 is a fourth. A fourth times a half is an eighth. So this would have to be a 3. And that's logarithms. How did I enter? So that's all well and good. How do you enter these on your calculator? For that, we need something called change of base, right? So if you have a logarithm of base A and you're taking the log of something, I'll just call that P again, right? Now, here's the thing. There's an infinite number of logs, right? There's a log for every positive number that exists, right? Well, your calculator can't have an infinite number of functions, and this is changing. I'm actually finding that a lot of students' calculators, even just scientific calculators, have the ability for them to input the base number. So if that's the case, you don't even have to really worry about what I'm saying. It's still potentially useful, but the main way we use it is to plug logs into calculators, at least in school. So if your calculator lets you just put any number you want right down here for the base value, you're good. You don't need to worry about this. But if it doesn't, most calculators have 2 logarithms built in. They have log with nothing written, and they have ln, which doesn't even say log. This log, if nothing's written, this is implied to be a standard log, base 10. Oops, I put a 10 in there. Base 10, because that's that's the base number of our number system. ln is a special log. It is log base e, and e is a special number like pi. It equals approximately 2.72, but its decimals actually go on forever. This is a rounding of it. It's 2.7181. I don't remember. It's 2.72 is what we round it to for just like back of the envelope, rule of thumb type of stuff. Anyway, this number e comes up a lot in the type of stuff you'd use exponentials and logarithms for. And so it's nice to just have a built-in way to take a log base e on a calculator without having to do anything else. So there's a reason this exists. Suffice it to say, at least cheap or older calculators, many calculators typically only have these 2 logarithms built in, but we need to take all sorts of logarithms with all sorts of different base numbers. So we have a way to there's just a product of logarithms, and we could dig into this. This isn't, just like everything I show you, this isn't magic. It's not something that somebody just pull that, like, we can understand why this change of base works. We're not going to go that deep into it now because we're out of time. I just want you to know it exists. So if you can instead take a standard log or any log, natural log, whatever, of whatever you're trying to take the log of in the first place, so log of p. And then if you divide that by that same log, so I'm just using standard log here, of the base, this result, these two things will be equal to each other. So this is a way to use the standard log, or any log, to compute a log of any other base. So, as our example earlier, for that the problem that we were working on, I had to do log of 1.08 of 2.5. So I had to do log base 1.08 of 2.5. That's what I was trying to enter into my calculator. What I actually entered into my calculator was standard log of 2.5 divided by standard log of 1.08. That's what I actually entered in, and that's how I got my answer. It doesn't feel great to end the session with what I refer to as a magic formula. Suffice it to say, there's a very understandable reason why this change of base works, and we can go into that at some point. I fully expect to go through this logarithm stuff again when people are to actually address people's questions. There are a couple math questions though. I hope that gives you a sense of my style. I know I was really slow on these questions because there's nobody here to I don't feel any pressure to go fast because there's not anybody with other questions waiting. Just know that when, in subsequent weeks, once this starts gaining some traction, hopefully, fingers crossed, I will likely go faster on a lot of these. I won't go on so many tangents and things. And my hope is that there will be people in chat asking relevant questions, and that will sort of keep us focused, and that will inform me about what little side tangents are worth going on. I go off on those because I don't know necessarily what the people watching, what their background knowledge and foundation knowledge actually is. So I try to fill in the gaps that I expect are most likely, that I expect people are most likely to have, the people watching. But when we actually have chat and people asking specific questions, I won't have to guess so much about what those are. Anyway, we got to do some actual math today. I hope that's my plan for tomorrow as well, hopefully. Maybe we might even have some actual user-submitted questions. That would be fantastic. And then that'll be done with my first week of streaming. That's very exciting. Anybody who watches this afterwards, if you made it all the way to the end of this stream, appreciate you. But I appreciate everybody else also who stopped by for just a little bit or watched 5 seconds of this stream VOD. I will be back tomorrow. Y'all have a great day.